All right, guys. Hey, welcome to week 2. We've got not too much content, but a lot of diverse content in this chapter slash module of the course. So I want to hone in, even though we've got a lot of different things, kind of disparate ideas going on. I really want to hone in on Ohm's law because I feel like that's where most of the students get hung up. And I hope by the end of this very short video, you're going to find it's not that difficult. It's pretty self-explanatory once you understand the properties and the rationale behind it. So let's jam. Let's do this. All right. Okay, part one, we're going to be talking about Ohm's law. We're going to scratch talking about power for right now. I want to put that onto another section of the lectures. I really want to focus on this one concept. We'll talk a little bit about resistors, but we'll go back into it later. And circuit diagrams are just going to be a consistent theme from here on. So just pick up little pieces. You'll see this content come back up in the assignments throughout the course. All right, so let's recap first. We spent a lot of time, many minutes in the videos just to get to the point where we could start having a conversation about what voltage, amperage, and ohms are. So let's recap to this. Voltage is the pressure, it's the force pushing electrons through our circuit, right? We use the analogy of like the water tower. The more filled up it is, the more pressure is pushing water on those pipes further downrange. We also have this concept of current, which is the flow of electrons. It's the actual physical movement that's going on within our circuit. And then we have this opposing force that we talked about, which is resistance. It's the barrier to the flow. It's a barrier to the current. And that could be like kinking a hose if you're watering your lawn, or turning off a faucet, or lowering the faucet, something to that effect. So we got those three concepts down, and we're ready to move on. So let's take a look at our simple circuit. Anywhere where you see lines, straight lines or lines at 90 degrees represent a wire. You'll see these perpendicular lines here, and these represent the biases on a DC power source, a battery, and they represent the original voltaic pile, the first battery. And then you see this squiggly line here. And this symbol will always indicate a resistor, some component that works against the flow of current within the circuit. We're going to go into this further in detail, but let's bring it back, and those you can see are images of resistors. So if you recall, electrons flow from the negative terminal of the power source, right? The electrons are moving and trying to find equilibrium, and they're going towards that positive bias, the exact opposite end of the battery in this case. But at the same time, we can consider that there is a positive charge carrier moving from the positive terminal just as quickly and with the exact same force as the electrons are moving from the opposite side. And we're going to be using this conventional electrical flow, or this conventional electricity flow, for almost all the conversation that we have about circuits from here on out. It's the way that the general electrical engineer talks about circuitry and electricity flow, and it's what we're going to adopt from here on. It was just important to know what the mechanism was behind electricity in chapter 1. All right, Ohm's law. George Ohms, not George, German physicist and mathematician, started playing around with Alessandro Volta's original voltaic pile, and he was fascinated with the ability to store energy or store electricity and enact it within a system or a circuit. And he started developing his own equipment to study and measure it. And that's when he started to find out some very interesting and unique properties. He found that there was a direct proportionality between potential difference, right, the battery, the power stored in the battery, and the electrical current. And then he started to create these laws that were mathematical consistencies or relationships between what we now have the concept of current, voltage, and resistance. And these consistencies are so relevant even today that we use them frequently, all the time, to measure the different proportions of forces of electricity within a circuit. So let's go back really quickly. We've got current, voltage, and electricity. The measurement of current is in the amp. The measurement of voltage is the volt, and resistance is measured in the ohm, after George himself, right? Uh, we have unit abbreviations for the amp. We always use a capital A or a capital V, and then for the ohm we use the omega symbol. And then the symbols that represent the current, voltage, and resistance in our formulas are fairly consistent. We use I to represent current. I believe the reason we use I was because it was a moniker for intensity. Voltage is often represented in a formula either as an E or a V. I'm going to use V even though the book uses E. I went to school learning V. Almost everything that you find in a practical sense out in the field will you be using V. E is supposed to represent electromotive force, the force of electricity, right? That pressure. Um, just know that they can be used interchangeably. I'm going to try and consistently state a V, even though the book uses E often. If I do use E or V in tests or assignments, I'll put an E/V, so it's not too confusing, as if two characters weren't confusing enough. And then resistance is commonplace R. Okay, so you'll see that there's always a circle or a pyramid or some kind of representation showing the relationship of voltage, current, and resistance together. I'm going to use the pyramid or the triangle here because I mean that's used in the book frequently and it makes sense to me. And what you're really seeing in this relationship is what Ohm himself discovered, that voltage is proportionally equal to current times resistance. And it makes sense if you think about it. If the voltage goes up, if the pressure on an electrical system goes up, you'd expect that there would be more current, more flow of electricity. Likewise, if the resistance goes up, you'd expect that the flow of electricity would go down. Kind of like what we were talking about before. Or if you have a hose and you're watering your lawn and you kink the hose, you're adding resistance and therefore the water flow lessens. And we don't have to look far to find representations of this, right? Here on the bottom left hand side of the screen, you see a geyser. You see a huge force welling up, and that's going to cause a larger volume of water to come spouting out. Meanwhile, on the bottom right side of the screen, if you have a levee or some kind of dam system and it's stopping the flow of water or slowing the flow of water, you're going to see a lower current of flow. See, there's the water analogy again, on one side of the dam than the other. All right, so let's take a look at the formula in action because it's easy to get lost until you see a practical application for it. And once we start doing these problems together, I think you're going to see that the relationship, the consistency is pretty self-explanatory. So let's jam on this. Right here we've got a simple circuit. We see a 12-volt battery source, and then we see that squiggly resistor, and it's representing 4 ohms of resistance. What we don't know is how much current is running freely through the circuit from one terminal of the battery to the other with the resistance. So we know 2 pieces of this puzzle, and it comes to find out that's all we need. We know the force of electricity, we know how much resistance is pushing back against that force, and between those 2 measures we can figure out exactly what the rate of flow is going through the circuit. So let's take a look at this step by step. We know V is equal to IR. Our voltage is equal to current times resistance. So let's plug in our values. We know our voltage is 12 volts. We do not yet know the current flow. That's what we're trying to find out. And we know that the resistance against our push, against our pressure, is 4 ohms of resistance. So here we just have a simple algebraic equation where we're trying to find some balance, some equality. So if we could take 12 equal I times 4, and then we just balance the equation. You know, we cut 4 from the right-hand side, and we divide 12 by 4. And you can see that we have 3 amps, because that's how we measure current, of current flow through this circuit. All right, so let's do a couple of these together instead of me just clicking through it. Let's take a look at a couple problems here. We have a simple circuit. We can tell because it's denoted with simple circuit on the bottom. So for our first one, let's see, we've got 10 volts at our source. We do not know the current as of yet, but we know that we have 2 ohms of resistance. So let's use our formula and knock this guy out real quick. Our formula is V equals I times R, and let's just plug in here. So our voltage is 10 volts equal to I, yet to be discovered. And then we have 2 ohms as our resistance. All right, we just need to balance this simple equation. We're going to divide 2 from this guy, which means we have to do it on the exact opposite side. So 10 divided by 2, real simple here. We got 5 is equal to I. And when we measure current, we're measuring amps. So the answer is 5 amps. And that's it. We're basically taking these really simple balancing algebraic equations and we're just trying to plug in for the unknown. Let's clear this layer and we'll do it again. Let's say this time around we've got 15 volts and we do not yet know what our current is. We'll just put I in there. And then we have 3 ohms of resistance. V equals I, R. Let's plug in. We got 15 over here. Don't know what our I is, but we do know we have 3 ohms of resistance. So let's balance this bad boy. We're going to divide 3 from this side, do the exact same on the other. So that's 3. 15 divided by 3 is 5 equals I. And when we're talking about current, let's honor those symbols, and that's 5 amps. So we can get rid of this unknown I, and we can put 5 amps here. Pretty simple, right? Let's do one more. We'll leave nothing to chance. And we'll knock this guy out. Let's do 9 volts, like a 9-volt battery. We did 3 already. Let's do 3 ohms again. And we don't know what our current going through the system is. So we've got 9 volts of force. We do not know how much current is running through, but we do know it's pushing up against 3 ohms of resistance. So let's do that. Divide by 3 on both sides. That means we have 3 is equal to I, and let's honor that symbol there. Our current is equal to 3 amps. We can get rid of that question mark because we're too good. And that's pretty much it. We're just going to be balancing simple equations. It's going to get a little more technical when we start doing circuits in series and adding some other sources to it, but at its core, this is all you're doing. If you can remember VIR, you're set. You guys are good. All right, let's hop back into the lecture and see what else we got. All right, we just solved those 3 problems and handily. We just took care of it. But we also know that there is a proportionality to these concepts in an electrical circuit. So we can do more than just solve for a missing current. In fact, as long as we have either 2 knowns, the voltage, the current, or the resistance, if we know 2 of those, we can solve for the other with no problem whatsoever. Let's get into it and we will see. Alright, so we're playing around with missing current. Let's take a look at an unknown resistance. Let's do this. Let's go 60 volts here at our power source and a whopping 6 amps. That's going to be fun. And we have R1, which denotes one resistor, or the first resistor in our circuit, and the only resistor in our simple circuit, and we don't know the resistance. Okay, so what does this represent? Let's think about this instead of just solving the problem because we want to practically know what's going on. We know that we've got 60 volts of force pushing our charge carriers, whether that be from the positive terminal or the negative terminal. And the rate of flow is 6 amperes, 6 amps. With these two pieces of information, knowing how much force is pushing our electrons and how many electrons are flowing through a specific point in the circuit and the rate at which they're flowing, we can also decipher how much resistance, how much pushback, how much friction is going on within our simple circuit. And that's what we're going to figure out right now. VIR. So let's switch it up now. We know we've got 60 volts here. And we know that we have 6 amps of current. And we're trying to figure out what this unknown resistance is that's latent within our system. Well, just like when we were trying to figure out the current, we can do the exact same thing. Let's get the unknown by itself. We're going to divide by 6 here. We're going to divide by 6 on the other side. And that gives us 10 of whatever the quantity of resistance is. And we know that a quantity of resistance is measured in ohms. So with some assurance, we can say that there is 10 ohms of resistance within our circuit, just knowing the pressure that's being exerted by our power source and the flow of the electrons. Let's do another one. Let's say we don't know the voltage, but we know we've got 15 amps. We've got a lot of current. Our electrons are flowing pretty quick here. And we know that we've got 6 ohms of resistance. So let's whip out our handy dandy equation here and we'll plug in. We don't yet know voltage. That's fine. We'll put a V there instead. We do know we have 15 amps of current and we have a component providing 6 ohms of resistance. And then look here. We just got a simple straightforward multiplication problem. So let's do this. We know 15 times 6 is 90 V. Volts is equal to 90. 90 volts. Let's honor the symbols there. Boom. And that's our circuit. Let's do one more and we'll change up another portion of the equation and then we'll wrap this up, I think. Let's say we got 30 volts in our system. We do not yet know what our current is, but we do know we have 3 ohms of resistance. All right, let's whip it out. VIR, easy. 30 is equal to, we're not sure what I is just yet, but we do know we have 3 ohms of resistance. All right, let's divide by 3 on one side, which means we have to do the exact same on the other. All right, I is equal to 10, and we're talking about current, so that's obviously an amperage. 10 amps. We nailed it. So you see how this proportionality is consistent? I mean, that's why they call it a law. It's very consistent. As long as you know 2 pieces of information, you can figure out the third. And what's more, we'll find out in a couple of minutes here, we can actually identify the wattage, the amount of work being exerted by a system if we know 2 of these 3 pieces of information. All right, so let's get back into the actual lecture. Boom, and that's it. Ohm's law, which trips up a lot of students, you just nailed down pat in like 2.5 minutes. So good on you. Let's take this one step further before we wrap this video up here. We can make some reasonable assumptions with the knowledge that we have. We know that if V is equal to IR, or voltage is equal to current times resistance, that we can change this formula around at any time to make it suit our needs. If V is equal to IR, then we can say that I is equal to V over R, or R is equal to V over I. And that's why it really helps to have this pyramid there. If you just shift around the orientation of the letters, you can see, like, if we scratch out I, because we don't know what I is, you see V is conveniently placed over R. If we don't know what R is, we don't know the resistance in our circuit, but we have voltage and current, and you just scratch that out of the triangle there, you see that voltage is conveniently placed over I, and that just happens to be exactly what the equation states. Resistance is equal to voltage over current. So you don't need to know all of the variants of this. If you have this either VIR memorized, or you can picture this pyramid or this triangle in your head, you're going to do fine with any of the equations that you get faced with. So now that we know the formulaic approach, and we've kind of have some practical hands-on experience in manipulating the values to see what the missing pieces are, when we have these conversations about how voltage, current, and resistance play with one another, it makes sense, right? There's some sensibility to it. For instance, if we're talking about voltage is going up, right? The pressure of electrons, or the pressure of in our electrical circuit, is increasing, and we know that the current is not changing, then that must mean the resistance is also rising, right? We're putting more pressure through our hose, and we're not seeing any more flow of water come out at the other end. That means the resistance, that kink in our hose, must have gotten tighter. At the same time, if our voltage, our pressure going through the system, is remaining fairly constant, and we can see that our current, or the flow of our system, is going down, well, that must mean that somehow, some way, our resistance is increasing. And then one final practical example, if we notice that our voltage, our pressure in our system, is decreasing, but our current, or the flow within the system, is staying the same, that must also mean that any resistance, any barriers, have also been proportionally decreasing as well. And I keep using this analogy, but it just seems to work for me, and I hope it does for you too. If we've got our water tower, right, and that represents our voltage, our pressure, and we're looking at the amount of volume of water coming out the end of a pipe, the more pressure in the water tank is pushing water, the water should come out at a higher volume. It should come out faster. So more pressure, more voltage, more current. But if we have, a valve somewhere in the line, and we're slowly cranking the valve and adding resistance because we're closing the valve little by little, and the pressure is maintaining that consistent pressure, and we're seeing that there's less water coming out the end of the pipe, well, that must mean that the resistance is increasing, right? If we increase our voltage, or we increase our pressure, and the water is staying the same, then that must mean that the valve has been closed a little bit. And you can start to see it's like a three-sided seesaw. They're proportionally connected and consistent, so that the values have an effect on the other portions of the equation. And that's pretty much what Ohm's law is. We're going to get into a little more nuance in a future video about how there are some parts, some implications of Ohm's law that aren't readily apparent when you first look at it, but it's going to make sense if you understand this, that we have this balancing act between these three different components within our circuit system. All right, guys. Hey, thanks for joining me, and I will kick out the next video very shortly.